Okay, continuing with section 5.4, one of the early problems we did when we started taking antiderivatives is we looked at some problems called initial value problems. So we're just going to revisit those quickly in just the context of, instead of just antiderivatives, we can also think of it in terms of indefinite integrals. So here's an example. The problem asks us to find a function where dy dx is equal to x squared plus 1 and y of 3 is equal to negative 4. Now previously we just said, well, if we take the antiderivative of both sides, the antiderivative of a derivative is the original function. Our notation now is just going to be slightly different, and I hope it makes a little bit more sense than just saying all of that out loud. So if I drop down my derivative that I start with in the original problem, and then go back to 6th, 7th grade. As long as you guys have been looking at equations, you've talked about the idea that if you do the same operation on both sides, that balances the equation out and it's still true. So we could add 7 to both sides of the equation. As long as you do the same thing on both sides, legal. You could subtract 12 from both sides. You could multiply both sides by 6.5. You could divide both sides by 18. You could take the square root of both sides. As long as you do the same thing on both sides, legal. Well, today, for the first time, what we're going to do to both sides is we're going to integrate. So we're going to integrate the left side and integrate the right side. Now, as long as we integrate with regards to the same variable, so if I integrate both sides with respect to x, therefore the differential that I attach on both sides is a dx, legal. So what I'm going to do is integrate the left side and integrate the right side. Now you're used to seeing the right side. The right side, no problem. The definite integral of x squared plus 1, we know how to handle that. Add 1, divide by the new exponent, attach the variable of integration, so the integral of 1 becomes 1x, and then add a constant c. No worries. But what's new now is this weird left side. We have the integral of dy dx dx. Right? What I would like you to notice is that we have exactly the same differential in the denominator and on our integral. So therefore, since we have 1 in the bottom, 1 in the top, those two things are going to cancel each other out. So the dx's cancel. And then the basic idea of the fundamental theorem is that the integral and the derivative cancel, and the only thing remaining then is y. So on the left side, we just have a y. Okay? The remainder of the problem is exactly the same as it was originally. To find the constant c, we replace x everywhere with a 3, and we replace y everywhere with a negative 4. So when we do that, replace y with a negative 4, and x with a 3. What that allows us to do then is find the constant by solving for c. So 3 cubed divided by 3 is 9. 1 times 3 is 3. When I add 9 plus 3, I get 12. And when I move the 12 to the other side by subtraction, my constant is negative 16. And therefore, the original function, that would give us x squared plus 1 as a derivative and would pass through the point 3 comma negative 4 would be y equals 1/3 x to the third plus 1x minus 16. All right, so the same initial value problems we did 3 weeks ago or whatever it was, pardon me, we could once again use to find our function just with the concept of antiderivatives. That was the old way. Sorry, I meant to say indefinite integrals, using the concept of indefinite integrals. Okay? So I think it makes maybe a little more sense with the indefinite integral when we have the dy dx going on. If we don't have that, our other option, of course, for a derivative is the following. So here's a second example. If the second derivative of x is equal to 3x squared plus 1, and f prime of 2 is equal to 6, f of 1 is equal to 1, we could ask you to find the original function. Here the notation isn't going to be quite as nice, but what we're going to do is take our original problem and we're going to integrate both sides of it with respect to x. So we're going to integrate with a dx. That's saying we're doing everything in terms of x. So left side, we'll integrate f double prime of x, and right side, we'll integrate 3x squared plus 1. Okay, now it doesn't make quite as much sense now, so it's a little bit tougher. But when we integrate a second derivative, what we're going to get out is a first derivative. On the other side, a little more obvious. 3 is a constant. To integrate x squared, we add 1, divide by the new. To integrate a 1, we attach the variable of integration, then of course add a constant c. Okay, the 3's of course cancel, and to find out what the constant is, we're going to use our initial value relative to the first derivative, and we're going to replace x with 2 and the function with 6. Right, so we're going to replace x with 2, and we're going to replace the derivative with 6. So here we go, derivative with 6, and x with 2, so that'd be 2 to the third plus 1 times 2. And so when we add those together and move them to the other side, 2 to the third is 8, 1 times 2 is 2, 8 plus 2 is 10, and 6 minus 10 is negative 4. Therefore, our first derivative would be x to the third plus 1x minus 4. So we've gone from the second derivative to the first derivative, so we're halfway home. Now we're going to move from the first derivative to the original function. So once again, we're going to integrate both sides with respect to x, because that's the variable that we're working with. On the left side, the integral of a derivative is going to be the original function. On the right side, add 1, divide by the new. Add 1, divide by the new. Attach the variable of integration to the 4, right? To the 4, or the negative 4. And then add a constant c. To figure out what the constant is, use our second initial value, which was f of 1 equals 1. So we're going to get out 1 when we put 1 in for x. All right, so I put 1 in for x and I get 1 out for the function. And so now I have to solve for c. So let's see, I'll have 1/4, 1/2 minus 4 plus c. Let's see if I can do that arithmetic. 1/4 plus 1/2 is 3/4, 3/4 minus 4, 3/4 minus 4. Oh, Yoses Tana. Let's see, that'd be 5 minus 4/4, 17/4, I believe. Feel free to double check me on that one. And so if I go up to where I had the original function and replace c with our constant, our final function then, x to the 4th over 4 plus x squared over 2 minus 4x plus 17/4. Again, feel free to double check my arithmetic on that constant there. Okay, so we'll continue to do the initial value problems. We're just going to be using the indefinite integral notation. So it's just going to be a little bit different. And then that, of course, leads us to our other initial value type problem that we've discussed before when we were talking just antiderivatives. And that was the idea of rectilinear motion. And we're just adjusting our thinking a little bit on these again, just adjusting our thinking slightly. Okay, originally we talked about how we can go from position function, which we normally define as s of t, s is position at time t. And what we've talked about throughout the fall was that if we took a derivative, if this would stop jumping around, if I take a derivative, rate of change of position, what I get is velocity, which we normally define as v of t, right? And so what we said at the time was v of t is equal to the derivative of position, right? And then we continued that idea. And if we take a derivative again, which means we take an instantaneous rate of change, we get to what's called acceleration, which we usually defined as a of t. And so we were able to say that a of t was equal to the first derivative of velocity or the second derivative of position. Okay, so that's what we talked about throughout the fall off and on. And today we're just going to do it backwards. We're just going to work backwards. So that means if we start with an acceleration function, again, we usually think of it as a of t, we can go backwards to the velocity function. And what we're going to do is we're going to get to the velocity function by integrating the acceleration. And of course, if we can move from acceleration to velocity, we can also move from velocity back up to position. And so we usually will say the position then is going to be the integral of velocity. All right, so we can integrate to work backwards from acceleration to velocity to position, all right, or just velocity to position if you only want to go halfway. All right, so taking derivatives, instantaneous rate of change going one way, and going the other way, we're going to integrate. Okay, so we should be able to move in both directions. Okay, and so the problems we did earlier, and I just want to do another one just to put it back in everybody's head, was something like the following. If I gave you an acceleration function of t squared plus t minus 1, and I gave you two initial values, v of 0 is equal to 6, s of 1 is equal to 4, right? Then we can go from acceleration to velocity, just using the concept that velocity is going to be the integral of acceleration. We integrate acceleration to get back to velocity. So what we can do then is replace our acceleration function with what it's given as, so the t squared plus t minus 1, and then of course integrate. So add 1, divide by the new, add 1, divide by the new, attach the variable of integration, and add a constant c. But to find the constant, we can then use the initial value for velocity, putting in 0 for time, and getting out 6 as a result. So of course all of these 0 terms just boop, boop, boop. So the constant then would be a 6, and therefore our velocity would be overall t to the third over 3 plus t squared over 2 minus 1t plus 6. Right, so this is kind of our intermediate answer. We were able to go from acceleration back to velocity, right? But since we are also given a initial condition for position, we can make the next step and go from velocity to position. So position is going to be the integral of velocity. So for us, we're going to be integrating t to the third over 3 plus t squared over 2 minus 1t plus 6 dt. So here we go. We already have a 3 down in the basement, so when we add 1 and divide by the new, I'll also have a 4. Okay, on the second term, we already have a 2 down in the basement, so when I add 1 and divide by the new, I also have a 3. Then add 1, divide by the new, attach the variable of integration, and add a constant c. Okay? And then my initial condition again was, I'm just going to jot it down so it's right in front of me. The initial condition was position at time equals 1 is equal to 4. So position is going to be equal to 4 when time is equal to 1. So what I'll end up with is 4 equals 1/12 plus 1/6 minus 1/2 plus 6 plus c. Okay? And so when I solve this for c, I did not do this ahead of time, so I'm sorry for taking a little extra time. I'm going to do this quickly, or as quickly as I can on my calculator. So plus and minus 6. And again, feel free to always double check me on these. I got negative 7/4. I hope that was okay. I did it kind of quick. So if I did it correctly, then my position function would be t to the 4th over 12 plus t to the 3rd over 6 minus t squared over 2 plus 6t minus 7/4. And that would be my position. Okay. So I hope that's looking okay. Hope that's looking all right. So didn't want to make this video nearly as long, so I'm going to pause right here, but I am just going to let you guys know, for anyone who's watching, that there's one last thing that I want to talk through on section 4, but I'm going to save that for when I'm in person, so that we can talk it through pretty well, so we can kind of go back and forth a little bit on that one. So one last topic on section 4. So I'd like this one due not on Monday, but on Tuesday. Okay, so hope you have a good day, and we'll talk to you again soon.